He was the developer of the landers that James Cameron used in the Mariana Trench. He's emeritus of Scripps Institution of Oceanography. And Kevin, take it away.
Thank you. All right. And keeping posted on the clock, give me a 5-minute warning on well, I want to thank my co-authors right away, James Cameron, Larry Herbst of the cameras, Tim Baldwin, and Stephen Couch, who helped with the glass, which really made a huge difference in our ability to go deep and cheap, as Don Walsh likes to call it. So let's see here, carrying on. In San Diego, we were the home port for the Bathyscaphe Trieste. I got to know a bunch of these guys, including Andy Recklinser, Scripps graduate 1955, a fine gentleman, and I got to meet him before I got to know who he was, so I wasn't overwhelmed. That turned out to be a good thing. Jacques Picard is on the right, and these were the guys that made the first deep dive in 1960. I asked Andy why they did it, because, well, there was really no practical limit to how deep we could go, so we knew they were just going to keep asking us, so we just decided to get it out of the way. So we did it. And we have one gentleman in the audience, Bob Fisher, who actually scanned the seafloor acoustically, who determined and confirmed the deepest place in the world's oceans. So thanks for being here, Bob. Then 52 years later, roll forward, we had a chance to meet this guy, and amazing fellow, tremendous mechanical aptitude, great team builder, and full of passion and desire to do interesting things, and follow that basic human goal or desire to explore and understand. This is a woodcut from the 15th century when we thought that we as a people thought the world was flat. The earth was surrounded by a sphere that was pierced by holes, and those were the stars. And nothing being perfect, we understood that then. There would be these little gaps around the edge where the sphere met the plate. And if we could find one of those gaps, we could put our head through and see what the world really works like. And works beyond. So he was like Cousteau in the 60s, where he brought along some of the best scientists on the planet, and a great guy, just a ton of fun to work with. And so we had Patty Fryer come along, Doug Bartlett from Scripps come along, and I had the privilege of building some of the machines that went deep. So it was a different approach. The submarine was different, everything was different. It was a whole different way of looking at the problem. As Bob mentioned in the last talk, Cameron's submarine was designed like a canoe on end, so that we really traveled rapidly to the bottom, 11 kilometers away, stayed in vertical mode the entire time, and then dropped the weight and come straight back up again at a fairly good clip. He expected to do a round trip of 22 kilometers and maybe move horizontally 2 or 3. So he was designed really to transit rapidly in that vertical mode. And great talk this morning, Patty, about why trenches are important. Yeah, they are. It's an amazing place. It's a whole different earth down there. It's totally different than that little slag heap we live on up above the water line. That's the Japan Trench, the overriding plate to the left, and to the right is the subduction plate, creating that subduction zone of the trench. And some amazing things that come out of there. It's a really active site. And for many years, we couldn't even get down there unless you had a big boat, a long piece of wire, and a bunch of hydraulics and a big budget, so you could actually charge all this stuff off and get out there. You could use acoustics, you throw little hand grenades over the side and echo off the bottom to get an idea how deep it was. But it was difficult, if not impossible, and that's where the term unfathomed comes from. You couldn't really even get down there. But it's important because there's so many things that are happening down there. For example, earthquakes, the ring of fire, tsunamis, volcanoes, all of that stuff is because of the trench. And even though we couldn't get down there, the trench itself could come and find us. So we had this massive earthquake off Sendai, just in 11. And sure enough, here's your trench coming up to say hello to you. And the idea that we couldn't get down there and put seismic sensors down below was really unacceptable. We needed to do something about that. So I started working on this. Sometimes you get an idea, and sometimes the idea gets you. And working with guys like Brett Fitzer, the folks at Scripps, which I'll show a few in a minute here, we began bit by bit, increment by increment, building the component technologies that in aggregate allowed us to have the ability to go deep. So this is the very first camera system that I built. We named it Mary Carroll after John Isaac's wife. John Isaacs is a professor at Scripps, or was. Did a lot of good work in free vehicle technology, and I learned a lot from him and his team. He was a prolific writer and passed that knowledge forward. And on the right is a second vehicle we built, Bobby Ray, named after, we named it for Bob Hessler. And I don't think he really thought we were going to do it. So he said, if you name it, call it Bobby Ray. That's what they called me as a kid. So we did. And the idea that we could actually increase our payload by just adding another sphere on top. And you see the form factor that we were developing was a lot like what Cameron ended up with his submarine. It's going to transit 11 down and 11 back, and we wanted a small frontal projected area so it could really travel rapidly. Different vehicles for different applications. On the left is one we deployed in 11 that went down to about 5.7 kilometers. I used a benthosphere up on top, the TR6000 modified to carry a payload down below. And acoustic release system on the right is one we did later in that year in the Serena Deep. And Doug and I were out there. We met up with Hurricane Moifa, actually. So we lost Patty, too bad, but we actually demonstrated that the acoustic system that we had from EdgeTech would work. And we weren't sure about that, so we did belt and suspenders and had a backup timer on board. But the actual acoustic command did work. We tracked it all the way up to about 1,000 meters, closing in to recover it when Hurricane Moifa, it was actually a tropical storm at that time, closed in on us, and everything went whoosh, and we ran for our lives. So we learned that we could do it acoustically, and 2 months later we got a call from Cameron saying, you got any time to come play with us? I learned a lot from this man here, Frank Snodgrass, and you can see in the beginning of my career I was playing with 70-75 spun aluminum hemispheres, 1-inch wall, 24-inch OD. Just an absolutely great guy, chief engineer for Walter Monk. Dual release system down below, pressure compensated batteries. He really lights and radios up on top. I just followed that model. It worked really well, and just a terrific guy. Later on, I was kind of coming up with some ideas about how might I build this thing like a Lego set, make it a modular system. You want, for example, these checkerboard things are really light. So on the way down on the left, it indicates it retracted. On the right, something that drops down. And multiple payload bays down below. Began looking at it from that point of view. Frank taught me also, he said, have 2 releases and make them different. Because if you screw up one, you're probably going to screw up the other the same way. So, all right, words from the wise. So we had different kinds of releases. I think we actually had 3. We had an acoustic, a timer, and a GTR, galvanic time release. My wife saw this drawing, and she thought I was inspired by some of the totem poles in Alaska, and I couldn't really argue that I hadn't been, but there's some similarity. On the lander design, I looked at it as a pickup truck to the deep sea. It's really what I wanted. A big payload bay in the back, certain length, width, height, capacity, and you just swap out payloads in the back, and it would make it really interchangeable. You can bring on multiple payloads, reconfigure it simply at sea, and there you go. So that was really the concept, and Emily Elo, I gave her a little Tonka truck, and on her thesis defense, she actually had it up here when she was giving her thesis defense, but she bought into this idea. And really, it's really quite useful. We talk about free vehicles. Gosh, there's just tons of advantages to these things. They've been around. The idea really popped up in 1936. I think it was the first paper by Alan Vine and Maurice Ewing. And they titled it simply Without Winch and Wire, and all the things that might happen because of free vehicles. This is all documented in my paper. Excuse me one second. All right. Sort of get a little dry mouth, sorry. But the advantages include you have a larger pool of smaller ships. You don't need specialized ships to do these things. So you can really rent a fishing boat, and we have. And work out of smaller harbors like Arecibo in Puerto Rico instead of San Juan, which would get us closer already to the deepest place there. And you can do it at a time that's advantageous to you, not waiting for a UNO ship to come around sometime in the next 3 years on their schedule, which is difficult. And you can do it at a more modest cost. You can send these things down and have them undisturbed on the bottom for quite a while. Depends really on the self-discharge of the batteries and your patience. You can do it for like 6 or 8 years if you wanted to. But imagine an entire annual cycle in the deep sea, in the deep ocean trench, where it hasn't seen a sunrise or sunset in 3-something billion years. Multiple ballast release methods. A single ship can deploy multiple vehicles. You You can place instruments or samplers at specified horizontal spacings and different heights off the seafloor, so you come up with this three-dimensional model. Operators can follow descent or ascent by the sound ranging. And ballast is on the bottom and left behind, so you can actually find yourself in a mucky place or a rocky, craggy place, and your anchor will still release and come on up. More stuff, you can reconfigure it to whatever ship of opportunity is present. That could be a small vehicle for a small ship or a big lander for a big boat. And multiple payloads, test beds to try out all kinds of stuff, AUV technologies, ROV technologies, manned submersible technologies. You can do them all on a platform and a lander and develop that confidence and competence that you require before you go on. And in the area of manned submersibles or even ROVs, you can use your landers as scouts. Just scout them around and just check out the bottom and come back later to an area that you really find interesting. You can also ship them pretty much on an aircraft, any kind of aircraft, because you have no hazmat. Scrap iron is all you're using for an anchor, so you just buy it when you get there, so it's cheap. You don't have to ship it from here to there. And I like the idea of disruptive technology. It's actually so cool that with all due respect to Scripps and Woods Hole and University of Washington, you don't have to be a big guy. You can be the University of Guam or somewhere else, and you have full access to the deep ocean trench. I like the idea, too, that they're really easily reconfigured, so students who are coming up pretty fast behind us here have the opportunity to have new tools put in their hands so they can go off and explore. So I think for a lot of reasons, landers are quite capable. They're simple, buoyancy high, weight low, very self-stabilizing. They have this inherent stability. You know which way is up, which way is down. That's very useful. We did some work with Stefan Pausch. I don't know if he's here in the audience or not, with Nautilus Marine Vitrovex in his company back in 2000, 2001. We began proposing how to modify their tooling to make thicker wall glass so we could go true full ocean depth. Not all these guys that are whistling past the graveyard. Full ocean depth is 6 kilometers. There's another half ocean left out there in terms of depth. So we made them go deep. And they give you the ability also to drill and tap and spot face. Not tap, I'm sorry, just drill through and put penetrators and other kinds of things on there. Working with Subcon and actually Seacon and others to develop connectors specifically adapted to glass spheres. You can see that we can glue in a ring. That 3M, we gave them a prize yesterday for black tape and all kinds of things, but 5400 is a great adhesive to hold PVC to the interior of glass. We'll keep moving on here. You can bolt plates onto it, bolt things onto the plates. And it's really like a garage. You can put all kinds of stuff on the inside. It's really fun. And the glass is so good you can just polish it, make a great camera housing, which we obviously did. We did the lander build in San Diego, rented a place out in Miramar Road, just started building like crazy. We had 7 weeks to get this done. So we tested off the Scripps Pier. Nice engine block down below there, just needed some iron. You know, the ocean's anemic, needs a little more iron. We leave a little bit behind. And here we are in our first test cruise off of Point Loma, December 23. I told Jim we thought we'd get one done by Christmas, and on December 23, a Friday, we actually went off there and did it. And so I told the guys to take the weekend off, and we'll be back to work on Monday. But we did. We did a short dive, test dive about 30 meters with a tether on it, just to be sure. We also did one in the bay, you know, just making sure. Test, test, test. And then finally it was good, and we went off to 1,200 meters and let her rip. And she came back up, and there she was. And we're off and running. It's 14 feet tall, but I only like that last little bit out of the water, because anything that's out of the water becomes negative, and you might be able to flip. All right. Shot down to Australia. These things are supposed to be portable. They are. And set up down below to start building stuff. We did. Modified this to put on an arm that drops down, which Doug showed in the last session, but I'll show you again. We had 2 of them. Very easily reconfigured. Lights, camera, action off in the Tasman Sea, 1,200 meters. And we paired it up with the submarine. We actually used a lot of component technologies 3 ways: on the manned submarine, on the lander, and on an ROV. So it really demonstrated the interchangeability of that technology, including the lights and the batteries. Jim likened this more to a seahorse. He thought it was the closest analog we had in biology. And more stuff. So here's our main ship, the ROV over on the side, which they adapted. So we had manned vehicles, ROVs, and landers. Some more testing off the ship. Buoyancy high, weight low, inherent stability. The arm folded up for minimum drag on the way down. There it is, launched off of Papua New Guinea. To take away the buoyancy of the sphere at the bottom, we added weights underneath. And then Jim, of course, was also looking for the camera shots as well as the science, and gave us a couple opportunities to say, I want a shot looking like this, and that's the shot that we delivered. Off to Papua New Guinea, heading north towards Guam. Beautiful trench, right off the south of the island. Jim's big boat over there. A lot of active volcanoes. It's an active subduction zone. Here's actually a shot by the ROV of the lander and the submersible together. So we had all three vehicles at one time using similar technologies. A shot of the lander over there. And the video didn't really transfer in very well. This is actually a shot from the lander, from the sphere, looking over the submersible. And it gives you an idea of the quality or the clarity of the image that we were able to achieve. Another shot from the submersible, or I'm sorry, the lander, at these large amphipods that Doug described in the last session, and gave you an idea that you could really capture a lot of images and a lot of animals. And they came back up with all of our samples on board. Jim was very interested in what we found, as was Ron Allen, the designer of the manned vehicle. And some of the size of these things are huge, amazing. Ended the dive in Papua New Guinea, headed for Guam, the Mariana Trench, Guam, and the Challenger Deep over here. And there's an advantage of the landers. This is the vehicle, the ship we had for the manned submersible, and that's the lander one over there. So a little smaller, a little humbler, but it worked really well. Tested everything before we went. JPL had their gear on board. And the deep dive was on a clear day for about 4 hours. And Jim made his dive, made it to the bottom. It was awesome. And recovered. And then we went back with the lander and filmed at the bottom of the middle pond of the Challenger Deep. And you see here, life persists at depth. Core samplers on the front. We were catching amphipods. Returned to the surface safely. And we got it within about 50 meters of the boat. Then we took off for the Serena Deep. And the image here, the video, was of an arm dropping down on a spot that Patty Fryer had picked out. It was just an awesome place. So the video's not running in the transfer, sorry, but trust me, it was awesome. But here's the landing site that Patty picked out for us. And because the lander's floating directly above the anchor, we're independent of the slope. That's the true slope. And Patty suggested it's in the paper, but there's a whole lot of ideas of what might be happening here, of the geology that influences biology. And her whole string of hypothesis was really seen in this one dive. So it was really an amazing place. I'll go to sea with you anytime, Patty. It was really pretty awesome. And there was we had a lucky twist in the chain, and it gave us an opportunity to get a panorama, which Kevin hand stitched together in the best manners of JPL. But a lot of light, clear water, high-definition cameras. It was awesome. And we found the bearded rocks, which we actually saw some of the stuff floating up in the water column. And so we thought it was biology, and now we've actually identified it. Recovered safely, and we returned to Guam. Hooray for us. And that's my talk. So any questions? How'd I do? All right. Thank you very much.
Thanks, Kevin. All the speakers will be here afterwards, so if you have questions for them, feel free to corner them before lunch. Okay, our next speaker is Natasha Gallo. She's a PhD student from Scripps and Lisa Levin's laboratory. Biological oceanography is her specialty, and I asked her what she liked to do, and she likes to travel at sea and on land. So she's going to continue the story that Kevin's been talking on a little bit more outside the sphere, I guess.
Yes, exactly. Or the view from outside the sphere. Let's see. Great. So that was a really fantastic introduction from Kevin, because now I can tell you guys about the really interesting ecology about of the megafaunal communities that we learned about using the Deep Sea Challenge expedition and the results from 2 different trenches that were visited during this expedition. And first, I would like to acknowledge my colleagues, James Cameron, Kevin Hardy, and Lisa Levin. I would like to bring your attention to this image, which shows the Deep Sea Challenge submersible and the Deep Sea Challenge lander rendezvousing at the Ulithi dive site. And so this analysis will focus on what these 2 different types of deep sea technologies can tell us about the ecology of these really unique ecosystems. So deep sea trenches make up the deepest parts of the ocean, even though they only account for 2% of the deep sea floor. However, they make up 100% of the Hadal zone of the ocean, which is defined as being deeper than 6,000 meters. Because of the difficulty of working in deep sea trenches, however, the Hadal trenches remain one of the least understood habitats on Earth. So it was really exciting to have this data set to actually study the ecologies of these trenches in more detail. Trenches are characterized by being narrow and having steep slopes because they're formed by tectonic processes, and they have high bottom current velocities, which is different than the abyssal plain. Furthermore, they accumulate sediment and particulate organic matter because of their shape. So sediment and particulate organic matter gets funneled into the trench axis. Biologically, they're characterized by having high species endemism, meaning that each trench tends to have a higher representation of unique species. Furthermore, the organisms that are able to survive in these ecosystems must be adapted to extremely high pressures, and they must also be able to survive in very food-limited ecosystems. To understand the ecology of the world's deepest ecosystems, there are certain extrinsic as well as intrinsic factors that we should consider to understand what structures the specific communities we find in the different trenches. So these 4 that are circled in red are the ones that are most relevant for the analysis today. Surface primary productivity and proximity to landmass determine how much carbon actually makes its way all the way down into a deep sea trench. And these extrinsic factors determine intrinsically how much of that food is then available for the organisms that live on the deep sea trench floor. Another really important variable, an intrinsic factor, is the local depth of a trench. So Hadal trenches vary from 6,000 meters to the deepest trench, which is the Challenger Deep Site in the Mariana Trench, which is 10.9 kilometers. And so certain groups of organisms are thought not to be able to survive below certain depths, and so the local depth of a trench also affects the community composition that we see. The trench floor fauna is really composed of 2 different groups of organisms, the scavenging community and the epibenthic community. The scavenging community is the one we most typically study when we use baited landers to look at what sorts of organisms live in the deep sea. The epibenthic community is usually studied by using different methods. Historically, those methods have primarily been benthic trawls, and more recently, those methods have been ROVs and HOVs. So the Deep Sea Challenge expedition was a really neat opportunity to actually look at both of these communities together. And so since the 70s, we've recognized that below 6,000 meters, there's a pretty significant change in community composition. And so these communities are unique Hadal communities, and they're usually characterized by the dominance of groups such as cnidarians, polychaetes, amphipods, mollusks, and holothurians. They're also characterized by the lack of some groups. For example, decapod crustaceans have historically been noted to be absent. There are multiple feeding guilds that are present in deep sea trenches, and these include deposit feeders, which are very common, scavengers, detritus feeders, and predators. And very rarely have we been able to study both the scavenging community and the epibenthic community together. And the epibenthic community using the baited lander tools as well as the submersible to look at the communities of both the bottom of the New Britain Trench and then the community at the bottom of the Mariana Trench and the Challenger Deep. And so my colleagues and I set forth 4 hypotheses about the ecology of these different communities in these two different trenches. And so we were interested in looking at patterns of composition, diversity, abundance, and then the proportional size of amphipods in these two different trenches. And we predicted that in the New Britain Trench, the composition in terms of the higher level taxonomic groups would be the same for both trenches. We predicted the diversity and abundance, however, would be higher in the New Britain Trench, which is both close to land and is in an area of higher surface productivity than in the Mariana Trench. And we predicted, based on feeding efficiency things that have been reported in previous manuscripts, that in the Mariana Trench we would see a higher representation of larger amphipods because they would be traveling further in order to find food than in the New Britain Trench. And so this comparative sampling design using images from the landers and videos obtained from the submersible allowed us to do this side-by-side comparison. So the landers did one deployment to the New Britain Trench and one deployment to the Challenger Deep in the Mariana Trench. And same with the submersible, it also performed one dive to the New Britain Trench and one dive to the Challenger Deep in the Mariana Trench. And so when we first assessed this first hypothesis looking at differences in community composition, we found that in the New Britain Trench, the community had representatives of amphipods, holothurians, and decapods. And so here circled, you can actually see two small holothurians that after several hours of the lander being deployed also arrived at the lander site. In contrast to that, in the Mariana Trench, we saw a scavenging community that was only dominated by amphipods and did not have representatives of either sea cucumbers, which are the holothurians, or decapods that attended the lander. Furthermore, one of the really exciting findings from the lander research was that we were able to observe one of the deepest observed decapod crustaceans known to man at the moment. Prior to 2009, it was thought that decapod crustaceans such as crabs and shrimps are not able to live in hadal depths. However, in 2009, Alan Jameson and colleagues described the first prawn that was found living in the Japan Trench at 7,703 meters. And so these observations of these interesting prawn individuals, that we observed 22 individuals and 70 images, and so it actually seems that they make up a fairly considerable portion of the community here and are playing an important role in the hadal community. And it extends the depth range of this group by 500 meters. And they were observed swimming around the lander in Niskin bottle, but not interacting with the bait. So we believe that they're probably functioning more as predators of small amphipods that are scavengers as opposed to scavengers themselves. In terms of looking at diversity, we used both sequence information obtained by our colleague Greg Rouse at Scripps, who used the amphipods that were actually collected from the landers during the New Britain Trench and the Mariana Trench deployments. And so from the sequence results, we found that there were 4 unique species identified in the New Britain Trench. And there was one species that was not captured but probably represents a 5th species because based on its behavior, it looks more like a predatory amphipod. So that brings our total of species in the New Britain Trench up to 5. In comparison, in the Mariana Trench, there were only 2 amphipods that were captured and sequenced, and from analysis of the lander images, it appears that there were only 2 of these species present during the entire time. When we look at the relative abundance of the scavenging community, looking primarily at amphipods, we also see that the New Britain Trench has a higher abundance of amphipods than the Mariana Trench. The time since first image is on the x-axis, and then the total amphipods per frame is on the y-axis. And as you can see, the New Britain Trench, which is in blue, for the majority of the time has a higher abundance of amphipods per frame than the Mariana Trench. And I would just like to highlight how high these abundances actually are. Even in the Mariana Trench, we have times when we have about 250 amphipods in one frame. So this is, if it plays, a time lapse. So this is what was actually quantified. And this is a 30-second time lapse of 7 hours of images from the bottom of the New Britain Trench. Looks like it's freezing up a little bit. Okay. Yes, so the bait for the New Britain Trench was a chicken, and I believe for the Mariana Trench was a tuna. Yeah. And so for comparison, this is what the scavenging community in the Mariana Trench looks like. And again, this is a 20-second compiled time lapse of about 5.5 hours of images post-deployment, post-arrival at landing. And so what we see is a really clear bimodal distribution of amphipods. You have your large amphipods and your small amphipods. And so this allowed us to also ask the question about the relative proportion of large to small amphipods in the total scavenging community. And here again, the time since first image is on the x-axis, and the percent of large amphipods in the total amphipod community in each frame is on the y-axis. And what we can see is that for the most part, there was actually a lower percentage of large amphipods in the Mariana Trench compared to the New Britain Trench, which was counter to what was predicted. The only time when that is not the case is at the very, very beginning of the bait arrival time during the first 40 minutes. And from here we can see that the large amphipods arrived first at the bait, and that is something that has been previously described in the literature. Because they're faster, they can move further. Because they're larger, they can move faster and further. And so now we'll switch over to talking about how these same trends show themselves in the epibenthic community. And so all of these results are based on the submersible video analysis that was performed. And so I can only show you very few results because of the time limitation. But so we're going to look at the same exact questions, but now looking at this other type of community in these same exact places. And so first we're going to look at community composition, and we wanted to know if the relative composition at a higher taxonomic level is the same in the New Britain Trench community, epibenthic community, as in the Mariana Trench, Challenger Deep epibenthic community. And what we can see is that in the New Britain Trench, you had a really rich community. There was representation of a lot of different taxonomic groups. So we had representations of xenophyophores, ctenophores, scythozoans, which are jellyfish, actinarians, which are sea anemones, polychaetes, echiurans, amphipods, of course, asteroids, which are sea stars, holothurians, and then also enterocnus, which are acorn worms. And so some of these images on the right show some of the species and fauna that were really characteristic of the New Britain Trench epibenthic community. However, when we look at the Mariana Trench, we actually see a community that is fairly deplete with very few taxonomic groups actually being represented. And so here we only see xenophyophores, amphipods, of course, because they're everywhere, and holothurians. And so these images at the bottom show some of the xenophyophores that were commonly observed at the bottom of the Challenger Deep, and then also some of these holothurians that were observed in the Challenger Deep. When we look at diversity patterns, we also see that for the epibenthic community, the diversity is much higher in the New Britain Trench than in the Mariana Trench. And we can see that both looking at total species richness as well as looking at the average number of species per sample. And then we can also ask these same questions looking at the abundance of epibenthic fauna in the New Britain Trench and the Mariana Trench. We can see that when you look at the average number of individuals quantified during a 2-minute video sample, the average for the New Britain Trench is much higher than the average for the Mariana Trench. We also see this in terms of the maximum number of individuals ever seen in a 2-minute sample and the minimum number of individuals ever seen in a 2-minute sample. And both of these values are higher for the New Britain Trench than for the Mariana Trench. And the really high abundances in some of the samples of the New Britain Trench were actually due to these really abundant communities of beautiful hadal, white-stalked sea anemones that were present and growing on the steep slopes of the New Britain Trench wall. Meanwhile, the Mariana Trench benthos was fairly flat and was pretty much characterized by xenophyophores and holothurians. And so just to summarize the results, in terms of the composition, we saw that there were significant differences in the composition at a higher taxonomic level of the communities seen in the New Britain Trench and the Mariana Trench for both the scavenging community as well as for the epibenthic community. In terms of diversity, we saw for both the epibenthic community and the scavenging community that there was evidence of higher diversity in the New Britain Trench compared to the Mariana Trench. And for abundance, we also saw higher abundances in scavengers and epibenthic organisms for the New Britain Trench than the Mariana Trench. And surprisingly, we saw that the Mariana Trench did not have a higher proportion of larger amphipods compared to the New Britain Trench, but actually had a higher proportion of smaller amphipods. And so one of the things that this type of analysis really lets us get at, which is pretty unique, is if the patterns that we see in the scavenging community hold up to the patterns that we see in the epibenthic community. And I think based on this analysis, we can say that actually, yes, they seem to. And to go back to our very first slides about the extrinsic and intrinsic factors that govern what sorts of communities are present in these hadal trenches and why we see differences in communities, we can talk about the intrinsic factor in the Mariana Trench, which is depth. So that's at 10.9 kilometers, where organisms are sustaining more than a ton of pressure per square centimeter. In comparison, the New Britain Trench is only 8.2 kilometers deep, so that's less pressure that they're sustaining, and that difference may be significant for some organisms. Furthermore, the amount of autochthonous and allochthonous input that is entering both of these trenches is very different. The New Britain Trench axis is only 60 kilometers from a land source, and so a lot of allochthonous matter actually gets washed out into the New Britain Trench. And this coconut, which was sitting at the very bottom of the New Britain Trench, is a pretty good example of that. Furthermore, the New Britain Trench is in an area with high overlying surface productivity, whereas the Mariana Trench is in an area of oligotrophic water, so very low surface productivity. And all of these things mean that the communities have to adapt to live in those conditions. And so these are probably the main drivers that give rise to these differences in both the scavenging and the epibenthic communities. And with that, I would just like to acknowledge the National Science Foundation and the National Geographic for the funding that made this possible, as well as Doug Bartlett and Ralph Pace, Doug Bartlett was the chief scientist on this expedition and has been instrumental in helping me analyze this data. And then all of the experts who helped me with identifications, as well as expedition support, Chris Simons, Ron Alum, National Geographic, and of course all of the crew members. And so with that, I will take questions.
We're getting a little closer to being back on time, so we'll hold off any questions till afterwards because we are webcasting this and we'd like to try and stay on time as close as we can. For our third presentation, we're going to continue with about the Deep Sea Challenger, basically the next steps. Anthony Tarantino from Woods Hole is going to be making the presentation. So Anthony, you got it. Thanks.
Yeah, I was just closing out some of the other things that were hanging around. Almost there. Excuse me. Okay, well, I'm Anthony Tarantino from the Woods Hole Oceanographic Institution. All these presentations this morning have been a great lead up to my presentation because I'm going to talk about what's next for the Deep Sea Challenger. What's going on? What is its next life? What can we do with it? I realize the missing little piece of information is a lot of detail on the vehicle design and the operations, the mode of operations, but a couple of slides in, presuming my video works, I can get into that just a little bit. But really what I wanted to focus on is what we're doing at Woods Hole with the vehicle and what's next. So for those of you who don't know, Woods Hole is in Cape Cod, Massachusetts. There's about 1,000 employees, most of which are scientists, but there's also a handful of engineers. I happen to be one of those engineers. I've been lucky enough to work on some manned submersible projects. I'm an Alvin pilot. I've also worked as an assistant project manager on the Alvin upgrade project, and I've been working on a different submersible operations project off of the RV Aleutian. So us engineers provide access to the sea for a lot of those scientists at Woods Hole. So how did we get involved? After Jim Cameron's historic dive, he wanted to keep the program going and wanted to make sure that the vehicle had a proper home. The engineers at Woods Hole have just gotten through a major Alvin upgrade. So we had roughly 30 to 100 engineers who had just gotten through some of the very same engineering challenges that Jim and his team had overcome to enable that vehicle's design and fabrication. So he came to us and asked us if we were interested, and naturally we said, of course, we'd love to take a look at that vehicle. So on March 15th, 2013, he gifted the vehicle to us along with all of its assets, so all of its spares. And we've been working with some of their project team to get access to all the technical information, all the technical data, along with some summary documents. In June of this year, after a long whistle-stop tour, the vehicle transited from from Santa Barbara overland through LA, Dallas, Atlanta, finally Washington, D.C., and made it to Woods Hole. So part of our project is not only focused on the technical portions of the vehicle, but there's also an outreach component to the project. We want to take advantage of the notoriety of the vehicle and the historic dives, and we want to use that to hopefully excite future scientists, future engineers, and highlight the need for ocean sciences and the need for trench exploration. So again, we've been working with Jim and his engineers, and we've been getting as much information on the vehicle as possible. So it really is an academic project for us. So we're going to turn all of our engineers loose, those engineers who had been working on the Alvin upgrade project, onto this vehicle, and they're going to take a look at what interesting things lie beneath. So right now, what's the status of the Deep Sea Challenger? Well, it's at Woods Hole. We've got it in our high bay, a high bay we typically use for Alvin upgrades and overhauls. But we do have the vehicle. We have a lot of spare parts and gear, and we've got 3 20-foot containers of support equipment that came with it. We've also got this interesting object in your upper right-hand corner, which is the simulator sphere that Jim used to prepare for his dive series, Jim and Ron Allum. The interesting thing about this sphere is it's completely outfitted. It's outfitted exactly the way the actual sphere is outfitted, so he would actually use that, he'd get in it, he'd do some simulated dives. It also came with a refrigerated room that was built around it to simulate the temperatures that he would see at depth. So Jim is pretty passionate about the ocean, as Patty probably knows. He's also very passionate about the technology, he's passionate about the vehicles, and he went through, he went to a lot of painstaking trouble to make sure he had accounted for a lot of the details, and that's really what we're going to look into over this next year. So, what are the objectives of our project? We're going to take a look at, again, all of these documents We're going to review them. And what we're looking for is novel technologies, novel operations, novel procedures, any sort of novel information that potentially has the potential to impact the technical and science community at large. What we are on the hook to do is look for that information and make it available to the general public. So through a series of talks like this, publications, and utilizing the new Center for Marine Robotics at Woods Hole, we're going to try and get this information out to the public. So hopefully they can use it and incorporate it to help out current and future projects. So we're also going to conserve the vehicle, so we're going to take care of the vehicle. One of the stipulations is we can't just cut this vehicle in half. Jim wants to make sure that we maintain its operational status. We want technically, we don't have plans to operate it. It's really a one-year project for us right now, but Jim wants to leave the door open for future dive operations if possible. So we're going to conserve the vehicle as we study it. And again, you know, the real objective here is to really harvest some of those technical advances that went into designing and building this vehicle. So Jim executed this project under a relative veil of secrecy. There was a few people who were involved who knew about what was going on, but I think to the community at large, we'd all like to know what went into that vehicle. So hopefully if there's some mysteries to be found, we'll be able to flush them out and let people know about it. So again, for us, it's really a one-year project right now. Out years are not quite determined yet. And it starts with a discovery and a review phase. So initially, we had a kickoff meeting back in June when the vehicle made it to Woods Hole. We sat down with a lot of their principal engineers, and we went through and reviewed a lot of the systems. Right now, we've got as much of the technical data package as we think we need to continue our review. We've been working with folks here in the U.S. and also their counterparts in Australia to compile the technical data and distill it. So our engineers are currently reviewing that information, and we're planning for a collaborative team meeting. So we're going to have a meeting in November with our engineers and Jim's engineers, and we're going to essentially present our findings to them, and we're going to take that opportunity to hopefully fill in the gaps in those areas where we feel maybe enough information wasn't provided. We're also going to take that opportunity to do a full ops check of the vehicle, so we'll power it up, we'll check all systems, we'll take a look at the structural integrity of the sphere, we'll make sure that all the systems worked as they thought they did, because they didn't strip down the vehicle. Essentially, after that last dive, it was taken into port, packed up, and sent over to Jim's house in Santa Barbara, where it sat for a year, essentially. So they didn't take an opportunity to pull it apart and just make sure that and do a full assessment. So we're going to do that in November. Finally, after November, what we'll do is try and target some key technologies and hopefully try and develop them further. So we'll look for some new applications, and we'll look to maybe improve certain things. Again, we don't really know what we're going to find. We're really in the initial phases of our project. So we've started to look, but we don't know exactly what we're going to find. We've already found some very interesting things, and hopefully we'll find more. So just a little bit about the Deep Sea Challenger team. They executed this project in two physical locations. They started it in Australia with Team Acheron, and ultimately they pulled a second team online in the U.S., and they split apart the vehicle design. As far as I can tell, Acheron did the bulk of the work, and the Earthship project, or the Earthship team, dealt with a lot of the lower pod work, so the lower pod, hydraulics, lighting, and some other portions. Really a testament to a great team. I mean, they did a lot of work. They got this vehicle assembled very quickly, and they got Jim not only to the bottom of the ocean, but they got him back. So that's always a good thing. And they had to overcome a lot of challenges. Again, challenges that we're familiar with at Woods Hole, because we've been doing similar things with our vehicle over the last 3 years. And we're really interested in all of this stuff. So transit time, we talked about the form factor of the vehicle. It's long. It's a canoe on its end. It's there to, it's made that way to optimize the travel times. Obviously, you don't want to take all of your time going up and down. You want to spend some time on the bottom as well. So that plays into energy as well. They developed some pressure tolerant lithium batteries, which warrant some investigation. And for the most part, all of their electronics were pressure tolerant. There were a few components in pressure cases, but for the most part, much of it was pressure tolerant. And they also dealt with an interesting issue in vehicle design where they don't have a rigid metallic frame. They actually used flotation, a structural foam, new type of structural syntactic foam, to really change the way I think vehicles, or it could change the way future vehicles are designed. So really, I mean, they deserve a lot of credit for getting this project done. All right, so keep your fingers crossed. We'll see if this video runs. So this is an animation that was provided to us by the Cameron team, and it shows the vehicle coming together. So it's an 11,000 meter BV sphere with axial inserts for the hatch and the penetrators. There's 4 penetrator holes. 3 of them were electrical penetrators, and 1 of them was an optical penetrator. But here's the real nice part. So here's that structural foam body. So in lieu of a metallic frame, they came up with structural foam and built the vehicle off of it. This is a look at how they attached the sphere to the rest of the vehicle using straps and tensioners. And then, interesting to note is the structural I-beam makes it modular. So these are battery packs, and if you look, they can actually go anywhere on the vehicle within that channel. They did something very interesting with foam to serve as a fire suppression system for any potential catastrophic failure with the batteries. And they had a full propulsion system, which allowed them to work in all 3 axes. Main lift point. And LED lights, all designed by the project. Power distribution, again, a lot of pressure-tolerant electronics in there, all pressure-tolerant electronics, and a top lifting point. So this is the communication mask / upper pod, which includes all the comms, all the navigation, but also a stabilizer fin on the top and bottom. I don't think the bottom one's shown here, but that was an interesting way to tackle some of the hydrodynamic issues that they had in the vertical direction. Lower pod, ascent weights, light booms, hydraulics and manipulators for sampling. And then a little bit closer look at the lower pod. So you had a sampling bay down low, and you had these light booms with cameras, high definition stereoscopic cameras with a science pod that allowed them to take samples, do push cores. And they also had an option of being able to deploy a mini ROV from the science bay. I don't believe they did that many times, but that was an option. And then releasable ascent weights. So, I mean, when you look at the vehicle, it's really very interesting. Typically, a vehicle like Alvin would have ascent weights and descent weights. So our prime mover in the vertical direction is weights. But typically when we get to the bottom, we drop some weights. Something interesting about this vehicle is they calculated their weight and balance such that they added just enough weight such that when they got to the bottom, they would be neutrally buoyant. And then when they came back, they just dropped them. And they ended up reaching speeds of up to 200 meters per minute. So it's pretty interesting for us again. So technologies that we're looking at right now, just key technologies that we're focusing on are battery, lithium batteries. I know we got some sweet guys here who are developing the same stuff. We're interested in looking at how they tackled that challenge. Imaging. Imaging here is really the form factor we're looking at. It's a very small camera, capable of 11,000 meters in depth, and being put very close together to simulate your interpupil or ocular distance, so you can get good 3D imaging out of it. I think they got some great 3D imaging. Illumination, they came up with their own LED lights, so it's something else to look at. And really something that hits home with the Alvin project is the life support system. They had a couple of people working very hard to get their life support system going, and they had some very interesting data that we've seen already that could actually directly apply to the Alvin upgrade. And finally, that structural foam. They were able to build the structural foam. They were able to build very large blocks. I don't know if you guys are used to how foam comes together, but typically there's a lot of wastage just when you're making raw foam blocks. And I think they came up with a way to really avoid a lot of that. And again, it's a structural foam, so you could actually hit this foam with a hammer and it won't break. So it's really interesting. So again, there's a lot there to look at, a lot for us to do. We're going to take 1 year to do some of this stuff. We're going to try and make it public. We're going to hit UI. We're going to try and publish some stuff in our documents, and again, in some of the publications. And again, we're going to try and work this into our Center for Marine Robotics over at Woods Hole. But stay tuned. So there's not a whole lot to give you right now other than what we've observed, but stay tuned, and hopefully we'll have some more information in the coming year. One last thing. One of the questions I get a lot is, when's it going back in the water? So again, this is a 1-year project for us. And as a former Alvin pilot, well, I guess I'm still an Alvin pilot, my answer for that is I would love to get it in the water as soon as possible. And we talked to Jim about that. There are some things, some constraints to doing that. I wouldn't rule it out right now, but I wouldn't expect it in the next 3 to 4 years. But again, Jim wants to leave that door open. We're more than receptive, and we'd certainly love to help him get it back in the water and hit some of those other dive sites that he wasn't able to make it to. But that's it right now.
That's great. Should be some exciting times dissecting that vehicle, seeing what Jim came up with. We're going to move right along now and try and stay as close to on time as possible because lunch is following this next presentation. And so I'd like to introduce Jinping Shi from the National Deep Sea Center in China. He's going to educate us on the Jialong submersible, and which is operational now. I was able to climb over it in Wuxi when they were developing that vehicle, and it's a very impressive system.
Where's the display? Your full screen? No, full screen. No, you cannot.
What happened? Did we close something?
Here, no, let's do that. Oh, this is a PDF, that's why.
PDF.
Right, you might just have to bring it, pull it over here, I think, right? Where's the which way are we going? There it is. Now, if you want, you can just pop it up here.
There it goes.
For
I don't know.
we full
We'll
screen.
just fit it to page.
Okay, so have to watch it there, I guess.
Okay, thank you. Okay. Good morning, everybody. Before this talk, first of all, I'd like to say thanks to Kevin Hardy, who got me on board at the last second. You know, at first I said I'd just make a poster. He said you should make a talk. So I'm a little nervous about this. And I'm from National Deep Sea Center, and I'm the visiting scholar of Center for Ocean Technology in University of South Florida now. So it's very convenient for me to have the chance, and lucky to have the chance to give a talk. Now, today's talk is not the research, not the technologies. I will tell you a story about 3 days for Jialong mine submersible. Jialong's yesterday, today, and tomorrow. Yesterday's story is about the R&D and the sea trials, and today's story, I will tell you this year's campaign with 3 legs that carried out in South China Sea, Northeastern and Northwestern Pacific Ocean. And tomorrow's story, I will tell you the home of operation and management submersible, my institution, National Deep Sea Center. And apparently and actually, Jialong program is not only a platform R&D, it's a huge project full of hardships and difficulties during the past decade. And several agencies in the world, in and abroad joined this R&D, and we have to outfit a research vessel to be the support vessel, and also we have to move the A-frame on the deck to be the large to deploy and recover the system. Also, we have, at the very beginning of this program, we selected and trained the pilot. This is enabled them to join the whole process of the program, and it's easier for them to get familiar with the system. Also, my institution, National Deep Sea Center, is planned to construct it for the home of Jialong. There are 3 milestones or timelines for Jialong mine submersible. We used 6 years from 2002 to 2008 for the R&D, and for the past 4 years, from 2009 to 2012, we did the sea trials. And from this year on, we came to a new phase named test operational phase. This phase is a transition from the sea trials to the real application. You know that a new support vessel is under construction for the submersible. Also, my institution is still under construction. The infrastructure hasn't completed, so it's a very important transition from this year on, the test operational phase. And as most of some may much familiar with the configurations or the parameters with the submersible, the operating depths, the dimension, the window diameter, and the power supply, the others. And it has some basic functions of the current submersibles. Also, it can cover the 99.8% of the world's ocean, and it can hover to operate to certain target, and it can facilitate the pilot's operational work. For if they made the flat bottom, they can use the automatic cruising. Also, there is the acoustic communication, and there is the SAT scan sonar, which can guide you the high-resolution bathymetry data. The sea trials were carried out from 2009 to 2012, and the fall sea trials was carried out from 1,000 meter to 10,000 meter, from shallow to deep. And I joined the last two sea trials. And the first two sea trials, I heard that it's a hard time for them. You know, we met a lot of difficulties. We met the alarms. We met the force. It burst off many times, and we solved them by patience. And finally, from the 3,000 meters sea trials, the submersible's performance becomes much more stable, and we knew it better and better. And at the below of the slide, you can see the support vessel, Xiangyang 9, and the Jiaolong Man submersible. During the sea trials, we validated the performance of Jiaolong, and also we got some initial scientific investigations. We got samples including the creatures, the sediments, the rocks, and also we got the water samples. We got very high resolution videos, pictures, and we got the bathymetry scan sonars data, and we deployed the markers. From this year on, there was a campaign with 3 legs just finished and led by the director Liu Feng. He's the commander-in-chief of this program, and it just arrived at the port days ago. So I will give you a description for this year's cruise. And 3 legs. The first leg was carried out in South China Sea, and the following are carried out in Northeast Pacific and Northwest Pacific, respectively. The first leg was focusing on the cold sea and the seamount area. The second is focusing on the COMAS polymetallic nodule contract area with the International Seabed Authority. And the third leg was carried out, was focusing on the COMAS cobalt-rich nodule contract area. It's different from the former sea trials for this cruise, you know. It's an important transition from the sea trial to the real application. Also, the duration is very long. It's about 113 days. There are about 20 scientists have the chance to get on board to do the research, and a dozen of them got the opportunity to dive to the deep. Also, the dive mission, we pay more attention to the scientific research. There is a brief description for the 3 legs. The first leg's target is the LBL positioning, and we provide support for the a very key project of National Science Foundation, the South China Sea Deep. It's led by the Tongji University. And achievements, we got a very high efficiency dials, and the LBL positioning was validated, and also a long distance cruising. Also, we investigated large areas cold sea. The second leg, the main targets were doing the biodiversity survey and the polymetallic nodule coverage assessment. And the achievements are as follows. And we did dials at 4 different areas, includes the polymetallic nodule contract area, the Weiyuan Sea Mountain. It was named by our country, Weiyuan Sea Mountain, and International Seabed Area Special Environmental Protection Area, and the agency areas. And the 6,000 meter level dives within 12 days were carried out. So that means, you know, the dives was very compact, and the performance of Jiaolong is stable. And the third leg, the main target was we did the biodiversity survey and cobalt nodules coverage assessment. We did deep dives in the Taiwan and the Taichi seamounts, and we got a very compact dives with 5 deep dives within 6 days. So the flexibility of the Jialong was validated. It can climb the mountain, sea mountain, and it's hovering to do some operational work. And also, we use the SAT scan sonar to cover area for the high resolution data. The conclusion for the 3 legs, we validated the performance for the submersible. Also, its flexibility was validated, and we got rich samples, including the craters, nodules, rocks, crust, sediments, and the other videos, picture data. And I'm sure it will provide solid support for the marine scientific research and enable new and water discoveries. Now, tomorrow's story, I will tell you my institution, National Deep Sea Center. It is the home to operation and management of Jialong Mine submersible, and also the other national health facilities. And it was established in the year 2010. And its orientation is an open and multifunctional public service platform with the main function of marine exploration and exploitation. And it was affiliated to the Oceanic Administration, SOA, like NOAA here. And also it was guided by China Ocean Mineral Resource R&D Association, COMA, like the father and mother. Now I will give you the bird view of the location of my institution. It's, there are 2 islands, the Chai Island and the Cao Island. And I will give you another bird view from the other directions. You see, it's very beautiful. There's no pointer. Okay. Oh. Yeah, here is the Chai Island. Here is the Cao Island. And here is the land buildings. We had 26 hectares land areas and 62 sea areas. And this is the concept map of the construction. It's under construction now. And this is the academic exchange area. This is the office buildings for the research and office works. This is the functional support areas. These infrastructures include the testing pool, a very large testing pool, and a machine shop, electrical shop, a pressure testing shop, and also storage and the others. And there are antennas for the communication with the research vessels. There is a very large dock with the leading jetty about 420 meters. And the dock is about 300 meters, so it can accommodate around more than 5 big research vessels to rest here. Also at the back there, I missed one building. This is the accommodation areas. This is for the experts. Maybe there is one room for you if you visit my institution. Now the variants and musicians is you can see there is a deep sea exploration and exploitation, and we manipulate and operate the national heavy facilities. We focus on deep sea research and based on the state-of-the-art technologies, and we manipulate the Jialong Mine submersible. In the future, we are planning to design or to buy some AUVs, ROVs, and the research vessels that speak the specific orientation are as follows. You can see exploration, observation, exploitation, and heavy facilities operation and management, equipment purchase and renovation, also the pilots training, education and international cooperation. There are some facilities would be here, housed in my institution, including the research vessels, and the AUV, ROV, and HOV. In the future, we are planning to do something as follows. In the coming 3 to 5 years, the test operational application cruises will be carried out. And we are looking forward to cooperators for join our cruises. Maybe in the coming year, we will send invitations to the marine scientists and engineers abroad for the cruise participation. And the main areas we focus on would be the cooler ship area, hydrothermal vent, and the Middle Ocean Ridge and the COMAS contract area. Okay. Finally, I'd like to quote one sentence from my institution. What we do is not cheap, just like Bob said that. And no single person, institution, or even a country can bear the whole burden and take the whole challenge. So we are proud and confident for what we are doing. And we also will be very happy to join hands with you to make the marine science and technology a better future. Okay, thank you. Any question?
We can take one or two questions before we break for lunch.
Okay. Harbor? Pardon?
Can your submarine hover above the seafloor and not drift?
Yeah, of course. It can do this work. Yeah, it can automatic cruising along the sea bottom, and it can hover in. Dynamic position, there is.
Any other questions? One more.
What kind of samples can you get? Do you get sediment samples, rock samples?
Yeah. Creatures, also we got the same creatures as you, but we use the fish, you know. I will suggest my institutions to use the chicken. Yeah. We got same creatures. We also got the sea cucumber. We will use the sucking sampler in the coming year. This year, this cruise, we didn't use that. Yeah, but we got the sea cucumbers and the others, all kinds of creatures. Yeah, maybe I will show you next in the future the creatures. Okay.
Okay. Thank you very much for your presentation. This concludes our session.